invitation. I was supposed to come here for a longer period, but things got really complicated. And then I'm trying to fill in slots where I can travel. This year has been particularly hard because I've been more than a year out away from home. And at most I stayed 3 or 4 weeks here in my place. So I miss my home. I miss my floor. I miss my stuff, walking around and doing nothing. Anyway, so finally I was able to get time to come over. Then next week I go back home and stay there a few days, and then again I travel back for 2 weeks. And then I start over all these things about panels and all these proposals to referee, and really complicated. So I'm starting feeling that I should refuse to do anything and at least stay on for a longer period. Anyway, but this good life will end in January when I start my classes. So that's it. Okay, so I'll be speaking today about interstellar media. I'll be speaking about turbulence, bubbles and superbubbles. I won't go into details on the classical models for interstellar medium because we've basically been fought against those models over the last 20 years. And those models are basically models. And anything we do is wrong by definition. Say a numerical model is wrong because you have to do approximations and you are depending on the resolution of your computer. The theoretical models are also wrong. They are just an approximation of reality, and we need simple approximations of reality. Therefore, summing up everything is okay. We have to understand what's going on in the medium, in the interstellar medium, and from there, then we can take any conclusions. Okay, so there's 2 lines of thought. So you do the theory, which basically is working with a pen and a paper, and you develop one-dimensional models which you can integrate easily, probably 2-dimensional, not 3-dimensional. And then you just go into a computer and you try to translate your equations into the language of the computer and you do a simulation. Hopefully, your simulation ends up to give you the observations, which is not true, it's not going to happen. The simulations basically, at a specific time, give you some hint of the observations. But on the overall, the average properties have to fit the observations. So this is a very tricky job. So you have to manage theory and numerical simulations, and you have to bring in all the physics in, and all the physics in is very complicated. There's not many people in the world doing all the physics into a single problem. Okay, so I'm just going to tackle some issues here. I'm going to show you some simulation. I'm not going into details on the simulation. I can explain you later. But the point is to explain turbulence and then speak about bubbles and superbubbles, and on the end, I'm going to link everything into what happens in our neighborhood, which is a local bubble. And one of the things you do in interstellar medium when you do modeling is that you model interstellar medium, but we know what is happening in the local bubble. We know all the emission in the local bubble. We know the absorption in the local bubble. So what you have to do is to compare your model with the local bubble properties. So you have to model the local bubble within the turbulent interstellar medium. I'll explain you how this is being done. I started this back in 2003 by Dieter Brachard. He was actually is a long-term collaborator for more than 20 years. He actually was referee of my PhD thesis, and then we made an agreement while I was in the West, and that we should actually tackle the interstellar medium in a specific way and work out the local properties. So this led to several number of papers, and we'll end up with an achievement in 2016. Okay, so I'll end up speaking about that paper, the results which match what happens in the local bubble with what observations of the ferromanganese crust in the seafloor. Right, so wherever you look in external galaxies, you see in H1 you see holes in this structure. So this is the SINGS survey, and you're able to see a lot of holes in all these spiral galaxies, and all these holes are produced basically by supernovae and clustered supernovae. And so the SINGS came up with all these results. So we have more than 1,000 holes identified in the galaxies. There's a relations with double type. So holes in both galaxies are larger than in spiral galaxies. That makes sense because your supernova has 10 to 51 erg of energy. If it is a small galaxy, the pressure effects, the counter pressure effects of the interstellar medium are smaller than in a big galaxy. Therefore, your bubbles expand larger. Holes in both galaxies are older than in spirals, of course, because they expand larger. They're too hot. They take a very long time to cool off. Energy input into the stellar medium is independent of the double type. That should be, of course. H1 holes can be used as a measure of supernova rate and stuff motion history. And there's 2D and 3D porosity determination of the ISM versus the bubble time. Okay, so if you look into this picture, which is LMC, Stephen Smith 1998, is a very nice picture in H1 where you actually can see a lot of structure. You can see holes, so you see LMC4, you see certain Dorados, but you see all these small holes, all this clumpiness structure, and you're able to see the body. Now, in low resolution pictures, the interstellar medium appears smooth and distributed in distinct phases. So you know molecular phase, cold neutral, warm neutral, and warm ionized media phases and hot phase. Now, what is interesting is that many of these phases are being identified relating to the atomic physics behind the processes, and that is collision, ionization, equilibrium. So these phases come up since the field Boltzmann-Abbe model for the two-phase model of the interstellar medium, where you basically have terminally unstable and terminally stable regimes, and all the material goes into the terminal regimes. As soon as supernovae come up, because it was observed at hot gas in the galaxy, then a third phase was introduced by Miguel and Stryker, actually by Don Cox and Randall Smith, and then Miguel and Stryker developed the three-phase model. Anyway, those models are based in this smooth and distributed medium, but they're not actually looking into a medium which is frosty, filamentary, clumpy, and it is not in pressure equilibrium. And it is a turbulent medium. And all these issues here just kill your models for Miguel and Stryker. Field goes the two-phase model, and so on. As I said in the beginning, in my introduction, these are approximations that you can use to understand interstellar medium. They actually are able to tell you certain values of pressure, density for specific conditions of the medium. They are able to speak about the global picture of the medium. So, for instance, the McKinnon-Stryker model, they'll tell you that you have a very narrow distribution of pressures, but if you look actually into turbulent medium, your pressure distribution is very wide. So I'll show you some plots in a minute. Now let's go to a IGALPHA survey, and this is observations towards 10 kiloparsec from us, and this is a picture taken by them. This is taken by Co and his collaborators, and they basically went over to this the data, and then they filtered the data, and then they applied to the data the genus statistics. The genus statistics is a statistics that allows you to understand if a medium is clumpy or if it is a whole medium, a medium like a Swiss cheese. And the genus topology has been applied since the 1980s for cosmological observations. Anyway, this was applied, so they applied genus to the data. So if then you can actually have these relationships where you just relate to the genus, and these relationships tells you if the medium is, if this AC is smaller than 1, then your medium is clumpy. And here you can see the genus distribution. Now you have a Gaussian distribution, therefore if your medium is Gaussian distributed, then it has this curve here. for the frequency and for the genus. Now, if you look into the parameter AC, you see that the parameter AC is 0.66. You integrate all over the frequency, and that means the medium is clumping. Okay, if you look into simulations of interstellar medium, so I was in Korea by the time, and then I provided my simulations. They went over to the simulations, and they made exactly the same procedure of filtering the noise and so on from the data, and then they applied the genus. So this is the picture from the simulations. This is the corresponding data, observational data. These are the corresponding genus curves for the observations and for the simulations data. And you can see the genus are similar, with different, a few small difference, which is telling you basically that your representation of the medium by this type of simulations is, in terms of using the supernova-driven turbulence, is more or less quite approximate. It is quite similar to what is happening in the galaxy. Okay, now as a medium, as you can see, the medium is turbulent, and let's see some things about the turbulence. So this is Navier-Stokes equation. This is a advection term on of the momentum equation. This is the viscous term. Okay, and so your viscosity is given by this, so it's 10 to 20 per cubic centimeter per square centimeter per second. And this is depending on your sound speed and your density of the medium. Now, if you divide this term here by this term here, you get the Reynolds number, which is a constant that determines how turbulent your medium is. So if the Reynolds number is small, your medium is not turbulent. If the Reynolds number is very high, then your medium is turbulent. Okay? So you see, so this number here, so basically this ratio here gives you a characteristic, corresponds to a characteristic velocity, characteristic length, and viscosity, and therefore making the calculations, you end up to 10 to 3 times Mach number times the characteristic length times density. So for a Mach number of 1 percent of characteristic length and 1 part per cubic centimeter for the density, you have a Reynolds number of 10 to 3, which means the medium is highly turbulent. Remember that the turbulent that you start turbulence around Reynolds number of 50, and before that you have a laminar flow. Okay, so for Mach number between 0.1 and 10, so your Reynolds number is going to be between 100 and 10 to 7. So if you consider molecular cloud and the average density for 100 parts per cubic centimeters, you're going to have a Reynolds number of 10 to 7. If you consider a density of 1 particle per cubic centimeter, so the average interstellar medium, and a Mach number of 3, which we know, then and a characteristic length of 100 parsec, you'll see in a minute where does this come from, you get Reynolds number of 10 to 6. Nevertheless, what this is telling you is that you really have high turbulent medium, and therefore you have to feed this medium all the time with energy. Now let's go into simple things about turbulence. So you basically inject energy at a certain scale, then that energy is going to cascade down to the smaller scales where it is going to dissipate. Now you know there's basically if you go into k-space, you basically inject your energy here, then goes down here. So here is your dissipation scale, and here is your injection scale. And so you're breaking up, you have a big blob, and then you're breaking up the blob into small blobs, and each one of them into smaller blobs, and so on and so on. So you're breaking up the larger eddies into smaller eddies, and while you're breaking up the eddies, you're transferring the energy into each one of the smaller eddies until you end up here at the smallest size possible for the eddies. At that moment, you have a small eddy like this. What's going to happen is basically one simple thing: vortex stretching. You just stretch your vortex and you dissipate all the energy. This is happening in 3 dimensions. Now, so here you can see the inertial range depends on the Reynolds number to 3/4. The dissipation scale depends on the viscosity, on the energy to 1/4, and the eddy lifetime depends on the temperature of your your plasma, and of course for hot gas it takes something like 1 million years, and for cooler gas it takes something like 100 million years. And this is quite important, what this is here, because this is telling you how much your medium mixes. If you look at your paper published in 2002 with Monica and Cloud, we showed that you cannot mix material or material. That takes very long time. While if you mix material at hot phase, that takes less than 1 million years. So this is quite important, how you actually have the end of lifetime. Okay, so let's see what happens in our interstellar medium. So you have a root mean square velocity of 10 kilometers a second for your turbulent motions. Now the dissipation rate is roughly this number here, 3 times 10 to minus 27 cubic centimeter per second. And therefore, assuming here density for cubic centimeter, root mean square velocity of 10 kilometers a second, and a characteristic scale of 100 parsec. Now, the dissipation time scale is basically dividing the energy by this dissipation rate, is roughly 9.8 megayears. For a scale of 100 parsec, the root mean square for 10 kilometers a second. So what this is telling you is that as soon as you inject energy into the system, you create turbulence, and if you do not do anything within 10 megayears, turbulence disappears. So you have to replenish turbulence with energy all the time.
Just a question, so this characteristic scale is the scale of the what?
Yeah. And you have to replenish the turbulence. Now, you would ask, how do I put energy into the system? Well, very simply. You have a supernova, so your star explodes, your shockwave propagates into the medium, compresses the medium, and you're transferring energy in kinetic energy to the medium. That's your transfer of energy to the turbulence. Okay? Right, so we need to have the system to pop up energy, and we have to find out the source of that energy. So if you pick up supernovae, frequency of 1 every 50 years, so 2 per century. If you assume that 40% of these supernovae occur in the field, randomly distributed, and 60% occur within an association, then you know that the fraction of energy that is transferred into the interstellar medium by that mechanism, or saying the expansion of the shock wave and transferring the kinetic energy, is roughly 10%, then you end up to have an energy of 2 times 10 to minus 26 gram per cubic centimeter per second. Now, this means, so this is the energy available for the supernova, the energy supply. But if you look into the numbers I gave you before, that you needed an energy supply for your turbulence of 3 times 10 to minus 27, then this number here corresponds only to 15%. This number corresponds only to 15% of this number. Okay? So what this simple calculation is telling you is that your supernovae are more than capable to provide the energy to your interstellar medium, to the turbulence. Now you would ask, okay, fine, can we have other sources of energy? Yes, we can. Here they are, the driving mechanisms. So supernova explosions, 2 times 10 to minus 26, stellar winds, 3 times 10 to minus 27. It's a order of magnitude lower. And then you have the other ones, protostellar flows, stellar ionizing radiation, and so on. So now you would say, okay, stellar winds would work. But that would mean that you would have a need of 100% of this energy to be introduced into the interstellar medium, which, of course, is not going to happen. So this leaves you to the only mechanism for supernovae. Right, let me just call your attention to an important thing which people confuses a lot, which is 2 dimensions versus 3 dimensions. So let me put the problem like this. You can simulate interstellar medium, you can reproduce observations with a 2-dimensional simulation. You can do this. You can do the same thing with 3 dimensions. The problem is, one is wrong and the other is correct. The one which is wrong is a 2-dimensional simulation. Why? Because turbulence is 3 dimensions. In 2 dimensions turbulence, you have vortex stretching. This comes up from the vorticity equation. You basically curl your Navier-Stokes equation on the left, and on the right side we have this equation here, and this is your vortex stretching term in 3 dimensions. In 2 dimensions, this term disappears. So in 2 dimensions, what happens is your eddies are being moving around, but they are not being stretched. Okay? In 3 dimensions, you stretch your eddies. So phenomenologically speaking, one turbulence in 2 dimensions is completely different than the turbulence in 3 dimensions. Okay. Actually, this plot is for 3-dimensional turbulence. You cascade the energy down. While in 2 dimensions, what happens is that you inject energy, part of the energy cascades down and the other part goes up into the larger scales, and what cascades down is entropy, which is vorticity squared. So this is completely different picture between 2D and 3D. So be careful about this. Okay, this is a simulation of interstellar medium. So I'm just showing you the simulation without explaining much. So these are supernovae and stellar winds here. You track down the formation of stars, you track down the winds, you track down then the explosion of each one of the stars, you track down the formation of microclouds, and then you just apply an IMF to a core which has enough mass to produce stars. And then you just track down all the stars. And we don't care about low-mass stars, we care only about supernova stars that generate, that become a supernova. Okay, one interesting thing here you can see, so red, this is density, this is pressure. Red is the hot gas, blue is the cold gas. You can see the stars exploding and the material expanding pretty fast within the bubble. So this is a bubble, then there's another, and so on. And you can see when the expansion occurs, there's relatively fingers expanding outwards into the medium. You can see in several cases, for instance here, there, and so on. But also you can see that within the bubble, material, there's a second explosion, and then the shockwave progresses, hits the material, goes into the shell, and then promotes turbulent mixing, and then you see material coming inwards into the bubble. Okay, this is quite important for instance what's happening here, because this is turbulent mixing, and turbulent mixing is faster than heat conduction. And there's a lot of confusion about heat conduction over the years because Spitzer's heat conduction, and people use heat conduction to explain how you could actually obtain oxygen 6 in interstellar medium, and it turns out that heat conduction, after it is established, you suppress it immediately. Okay, so what is important here to also to see is that your bubbles, if initially they're spherical, soon after they lose all the symmetry. And that has to do with the surrounding medium. So the hot gas goes where there's low density. And so you have non-spherical structures. Here, in the pressure, you can see the bubbles, you see the explosion, high pressure, so this is in log scales, 1, 2, 3, 4, and 5. And so what happens is that you see high pressures tend to fall, and then suddenly the pressure decreases pretty fast. Okay, so picking up from the picture, from the images, it's very simple to see what happens to the bubble. So you have a simple bubble, there's a surrounding medium here, there's a low density region. So what happens is that your bubble expands towards this region here, and then it breaks out. The way it breaks out corresponds to a jet turbulence. While if your bubble expands in a uniform medium, it expands until its pressure becomes equal to the surrounding medium pressure and breaks up the shell into filamentary structures, and this is kind of a grid turbulence. And actually you can see this into the simulations and can then explain all the behavior of the bubbles. Anyway, so here you basically transferring energy through PDV work, towards the surrounding medium. Okay, so we have two scales here. We have the injection scale, which is the characteristic length at which energy is injected. Basically, normally you say it corresponds to the size of your eddy, and the correlation length, which is the size of your structure which are all connected together. And from simulations, it turns out that if you run simulations over a very long period of time, and either hydrodynamic or LHT, and you calculate correlation lengths, you come over with a correlation length of something like 75 parsec. The longitudinal as well as transversal correlation lengths. And so this is telling you that your injection scales are around 75 or 80 parsec. Okay, as you can see here, there's a huge variation of time, and this has to do with being you having superbubbles. So you're sweeping your medium, and you're catching up all the correlation lengths related to small bubbles and larger bubbles. And so these are the cases where you have bigger superbubbles, and these superbubbles, they last for very long periods of time. Right, here, let's look into nearby bubbles. So this is the local bubble. So we have loop 3, we have loop 1 over there, loop 2, and inside of the local bubble you see the local fluff, which is material around the sun, and you have all these clouds here which result from the interaction of the loop 1 towards the local bubble. As stars explode in the loop 1, material interacts with the local bubble shell, and then due to relative instabilities, this breaks up and clouds propagate inwards. So these clouds where we are, local cloud and so on, they are the result of the breakup of the shell between the local bubble and the loop 1. Now superbubbles, now looking towards the galactic center, you see this is the local bubble, and it gives you the impression it is an open region here above and below. So this would be a chimney. And here you can see the Fucus superbubble, and this is hot material going up. So there's another chimney structure here. Right, so here you have the Dorian superbubble, very well defined. And basically, your superbubbles occurring will be associations, and the lifetime, typical lifetime is roughly 50 mega years, and their size goes up to 1700 parsec. Right, and the internal densities are around 10 to minus 3 cubic centimeters in the case of the local bubble, and 10 to minus 2 cubic centimeters in the case of the loop 1. So this is basically looking to our neighborhood. So here you can see our Fucus superbubble and the size it has relative to the galaxy. And of course, what happens to the superbubbles is that basically you inject metals into the thick disk and into the halo, and then this material is going to participate in the circulation between the halo and the disk. Okay, here is the local bubble, and here are the local cloud and so on, and here is the loop 1, and so this is cosine association, and this is a picture, X-ray picture, towards the interface between the local bubble and loop 1. And you can see here, this is the shell between the two, and then you can see the X-ray emission from the local loop. This is from a simulation carried out for the local bubble and loop 1. So you see the smallest one is loop 1, a local bubble, and the largest one is loop 1. And this was a simulation used in 2016 paper. Okay, so how was the local bubble formed? Actually, the local bubble was formed by the 17 explosions of stars from two moving groups, Upper Centaurus Lupus and Lower Centaurus Crux. And in their way, they passed through the present region of the local bubble, and then they went over and they exploded. So you know what are the missing stars in this groups of stars, and then basically you can apply an IMF and immediately you know what are the correct stars missing. So we basically assume one star per beam in the IMF. Right, so and the school sand, you know there's 81 stars were formed, there's gone already, and you have still 42 to go. And one more interesting thing is that when you have these stars going off, exploding, then you produce iron 60. And so a trace of the explosion is looking for the iron 60. And this can be seen in the seafloor interferon manganese crusts. There's these plates here, smaller structures, And these crusts are composed of 20% of manganese and 15% of iron. One of these biggest crusts was recovered, that's the crust 237 kb. And then they made measurements with mass spectrometry to determine the iron 60 population on the crust. Now, what is interesting is the mean time for decaying for the iron 60 is something like 2.6 million years. So, which means that you can track down the iron 60 in the ferromanganese crust for a long period. Now, here you have the ferromanganese values, ratios to iron, the iron 60 to iron ratio, and you can see this is the time scale on this crust, so you can measure here the distribution of the time, and then you can see that there are explosions occurring at different times over the last 14 mega years. And the nearest explosion, the explosions which have a largest iron 60 abundance occurred at around 2 mega years. So this means that these were the stars that approach more the sun. So basically, if you want to simulate these things, you basically know the stars that generate the local bubble, you know the stars that generate loop 1, and then you just set up everything in a turbulent medium, and you just let everything to evolve. Okay. So, and then you trace on the iron 60, and you take into account then the position of the iron 60 into the C4 and the passing through the atmosphere and the residing time in the atmosphere. And here you can see, on this plot here, these are the simulations for the iron 60 distribution, and you can see here the peaks of the iron 60 from the simulations, and you can compare here from the latest observations for the iron 60 the ferromanganese crust, and you can see the expectation of the iron 60 on the simulations overlapping the iron 60 distribution observed. And quite impressively, you are able to say what is iron 60 in the C4. Okay, let me just go before. On these simulations also, you can track time for different ions, because these are atomic simulations also, time-dependent evolution. So it is a snapshot of the oxygen 6 distribution. So this is local bubble, this is loop 1. This is at 13.6 mega years, this is at 13.9 mega years after the first explosion. And then you locate yourself in the sun's position, then you take the ones of sight observations. And these are the ones of sight observations here at different times of supernovae. On the points with the arrow bars are points from observations using fuse and Copernicus data, and you can see that the column density from these simulations is within the arrow bars of the observations. So basically, this is telling you this kind of simulations are able to reproduce also the distribution of the oxygen 6. Now, look, for specific lines of sight, you have different values, of course. You have to look into all picture together. Right, and if you look into carbon 4 to oxygen 6 and nitrogen 5 to oxygen 6, you also can compare this with observations. We know in observations there is no carbon 4 nor nitrogen 5 in the local bubble. That means that the ratios are lower than -1. And so if you pick up here for different times, that's 0.5 mega years after the last explosion, 0.6, 0.7, and so on, you're able to see here, so this is the fraction of lines of sight for carbon 4 to oxygen 6, and you're able to see there's a shift, so this is -1, so there's a shift on the column density, on the ratio towards the left, above 0.8 megayears, above 0.7 megayears. The similar behavior happens for the nitrogen 5 to oxygen 6 ratio. So in these places, the last explosion of supernova in the local bubble between 0.5 and 0.7 megayears. So we have 3 different indications. here. We have the iron 60 that shows that you had explosions nearby, and you're actually able to match those depositions in the sea floor using simulations. From the same kind of simulation, you're able to track down for the oxygen 6 and show the oxygen 6 distribution. And finally, you're able to track down for the carbon 4 and nitrogen 5 ratios to oxygen 6 and see they actually match with observations. Now, this is important, this picture here, because this brings me to the initial comment I made. Simulations are not correct, and every single simulation does not reproduce the medium, which is true. Therefore, you should have lines of sight which do not reproduce what you observe, because your observations are towards specific lines of sight, not overall volume. Okay? Right, to finish, my final remarks, your ISM is basically driven by supernovae. Your bubbles break out into the low density medium nearby, or then they disperse if the medium is uniform. Your superbubbles break out from the disk and launch their oil content into the seed disk and halo. And taking into account for the evolution of superbubbles, then you also should take into account for the missing stars. And then, in the case of local bubble, you actually should look into the iron 60 and go into the seed crust and look for the measurements there. Okay, before finishing, this technique here, counting for the missing stars, you can apply this, for instance, to understand the Fermi bubbles. But in the case of the Fermi bubbles, you are able to find out 10 to 4 missing stars and to have them a supernova. And therefore, the Fermi bubbles in the case is not produced by the correlated effect of 10 to 4 supernovae, but a combination of eventually some supernovae and the tidal disruption events of stars approaching the supermassive black hole, Sagittarius A star. Okay, thank you. Bubbles everywhere.